but they know I only need that Sunny Island system to ride through for X number of hours. They're making sure that a very expensive saltwater fish tank has the ability to run pumps and keep a heat light on, keep a freezer from thawing. They have some desire to keep a load running for a short number of hours. But any long-term grid outage, PV or a generator likely would be required. But again, the Sunny Island only needs that battery bank to operate. If there is PV in the microgrid, SMA is an advocate of AC coupling, and we'll talk about that in a few slides. But generally, we would recommend having a PV system with an inverter, having the AC output of that PV system meet on the same loads panel that will be called the protected loads panel as the AC output of the Sunny Island. So that is a very quick summary of what AC coupling is. Generally, the benefit of that is that a homeowner gets to use their normal AC appliances in an outage situation. They don't have to worry about DC appliances that may be more efficient, but generally costly and not as readily available. So SMA is definitely an advocate of AC coupling. So while someone can use PV and couple it via a charge controller onto the DC side of the Sunny Island, no PV modules will ever wire directly to the Sunny Island. So it is a battery inverter only. It obviously can take power from the battery to create an AC microgrid. So it can go from DC to AC, but it can also take AC power, charge the batteries via DC, so it can convert AC back to DC. So it's a bidirectional battery inverter. The US, Sunny Island US models, each device creates a 120 volt, 60 hertz waveform. We'll talk about clusters of islands where you can create a 3-phase grid or a split phase grid, but each device individually will create a 120 volt, 60 hertz waveform. The Sunny Island US has two models, the 4548 and the 6048. They look identical, so they both look like the device I'm showing on the screen. Looking at them front on, you wouldn't know the difference. The very few parameters are different for these two devices. The continuous output power is either 4,500 or 6,000 continuous watts. So that's the 45 and the 60 part of the name. The 48 is to signify that they work with a low voltage battery bank. The range of capacities of the battery bank vary widely. When we talk about the Sunny Boy storage, or when you hear people talk about batteries, they may talk about watt hours or kilowatt hours. For the Sunny Island, we reference the battery bank in sizes related to amp hours. Since that battery voltage is generally locked at 48 volts, you can multiply 48 by the amp hour numbers I'm presenting to get a watt hours number. So the stated supported battery size range is 100 amp hours to 10,000 amp hours. If you multiply that by 48, that's 4,800 watt hours up to 480,000 watt hours. So that's half a megawatt hour. That is a monstrous battery. That is a battery room. That is not a battery bank. So that is a huge, huge battery. And again, these are just suggested ranges. The Sunny Island can turn on with a much smaller capacity battery bank, as long as it has a stable 48 volts. But if it has to cycle that battery bank repeatedly within a day, the lifetime of that battery will be very short. So the lowest rational size for any real system, we think, is around 100 amp hours. When you use a lead acid battery bank with the Sunny Island, generally manufacturers of the lead acid battery banks don't want those to be discharged more than 50%. So that low end is not very big. The BYD batteries for the Sunny Boy storage can be 10 kilowatt hours, almost all usable in one box. So that the low end is a quite small battery bank and would be really capable of just running smaller loads, but the range is huge. Since this device was designed to be an off-grid device, it has quite a bit of surge capacity so that someone can start up critical loads that have a motor, some large current draw when they're starting up, a well pump, things like that, that require a very brief but high current pulse. Both models of the Sunny Island can provide 8,400 watts for 1 minute or 11,000 watts for 3 seconds. That's almost triple the nameplate of the 4548 for 3 seconds. So plenty of excess capacity to provide that surge current to start critical loads like motors or pumps. I'm showing now a very simplistic view of the wiring of a Sunny Island, and we'll show the device circuitry actually with the lid off on the next slide. But there are DC positive and DC negative shown here. Only the battery connects to that. Again, things can couple on the DC side, but that is the battery connection. The AC1 terminals are the AC terminals, line, neutral, and ground, to provide that 120 volt, 60 hertz waveform if the Sunny Island is taking power from the battery and creating that waveform. The AC2 terminals would be quote unquote upstream of the Sunny Island. That would be where an external voltage source, such as a generator or the utility grid, connect. If the Sunny Island is used in battery backup mode, grid power coming to the AC2 terminals can flow across the transfer relay that we show as open in this diagram and go to the AC1 terminals. So in battery backup mode, the Sunny Island will allow grid power to pass to the loads. It will pull off what it needs to charge the batteries, but it doesn't have to use battery power to power those loads. It can lean on the grid until the grid might fail. If someone is using the system with a generator, the generator would also connect to the AC2 terminals. There is only one set of AC2 terminals in the Sunny Island. So if someone is using this device as a grid-tied backup device and they have a generator, there needs to be a transfer switch outside of the Sunny Island that will switch the AC input from the grid to the generator, because the output of that switch still would wire to AC2. There's only one set of AC terminals coming into the Sunny Island. If somebody was using the Sunny Island off-grid without a generator, nothing connects to AC2, but that's not very common. This is a shot of the Sunny Island with that yellow lid removed. You can see the circuit boards there. I want to zoom into the lower left. That is where the AC1 and AC2 connections happen. The center right below the DC circuit breaker is where the battery wires. You may not remember my terminology for AC1 and AC2. Don't worry, it's actually printed on the circuit board below those AC connections. You can see it says AC2, the grid or a generator. That again is the external voltage source. And the AC1, it says loads, and if you can't read that, it says Sunny Boys. This is another example of SMA's emphasis on AC coupling. I said that we would recommend the AC output of a PV inverter be on the loads panel that the Sunny Island is providing power to when it's in off-grid mode. So that is, we're writing it there on the circuit board. The loads and the Sunny Boy breakers should be there in that loads panel. So that's the AC1 and AC2 breakdown. It's right there on the circuitry. To the lower right, you see a red arrow for communications and the relays and temperature sensor and dig-in. Dig-in is something I'm not going to spend time talking about, but it is important and must be wired if someone is using the system for grid-tied backup with a generator. Dig-in tells the Sunny Island when that external switch has changed the AC source from the grid to the generator. It actually changes some operating parameters in the Sunny Island, so it is required for that install. There are two relays in each Sunny Island that can be programmed to do certain functions based on potentially state of charge, based on time, based on what charging cycle the batteries are going into. So they're very, very useful. And again, there's two relays per Sunny Island. So if a system was using 4 Sunny Islands, you have 8 potential programmable relays to utilize. It's very, very useful, particularly for off-grid systems. The display of the Sunny Island is shown here with the up, down, escape, and enter key. All of the programming of the system is really done from the front of the master device. If you have more than one Sunny Island, one will be the master, all the rest will be designated as slaves, and they all just take commands from the master and run the system in accordance with what the master says. So really all of the programming is done from the front of the master device. The display, the lower line of the display shows kind of power flows. We see in this scenario, power is coming from the G, which could be the grid or the generator. Right now you see the utility pole right next to that. The grid status is good, so the G would be grid power coming past the Sunny Islands, perhaps recharging the batteries, and providing power to the protected loads panel. It's possible for that directions of those arrows to reverse. If there is PV or a small wind inverter on the protected loads panel, if there's excess power, the Sunny Island is set to allow that to backfeed past it back to the grid. That can be disabled so that there will be no grid backfeed. And when the input on the AC2 terminals is the generator, the Sunny Island will change to not allow any backfeed to the generator, no matter what the grid settings are. So the Sunny Island is very smart and will manage its power sources very efficiently. Some other stuff can be read right off of the front panel of the Sunny Island. So there's quite a bit of information that can be accessed through that display. The DC breaker, it's labeled as DC disconnect, you may see in this diagram. That is completely correct. This should be considered simply an on-off switch for the Sunny Island. Between the Sunny Island and its battery bank, there needs to be an external DC circuit breaker or fuse connection. If the DC circuit breaker, the one shown in this picture on the front of the Sunny Island, is in the off position, there is still voltage at certain spots on the circuitry inside. So this should be considered simply an on-off switch for the Sunny Island. The SD card right next to that should be, we provide SD cards for the devices. It is critical that the SD cards stay in the master. It logs all of the information of as many Sunny Islands as there are in the group at the master. And this is critical. If you ever need to call SMA service, every Sunny Island install is different. And unless service has that SD card information, it is near impossible for them to be able to quickly troubleshoot a system. But with that SD card information, it is pretty straightforward. So always install the SD cards, and there's no reason not to have them installed on all of the devices. We provide them to you. I don't want to spend too much time discussing AC coupling, but I do want everyone to understand what I mean by AC coupling. The screenshot shown here is coming from a video that we have on our YouTube channel. I believe it's called Energy Supply in Remote Regions, that shows really the reason of being for the Sunny Island. And it's showing a scaled up AC microgrid here, where there are homes with PV inverters that can contribute power, and also they're using power. You see a three-phase Sunny Island group with its battery bank and a generator in the lower left. So all of the AC power from the home's PV systems, from their loads, all of this is connecting on the AC network across the power poles shown in this diagram. It is far easier to scale up and expand an AC network rather than DC. So it provides power more reasonably to remote, longer runs of wires, and it allows homes to use very readily accessible AC loads. So we really believe in this AC coupling. And as this device was built to be able to create and scale up utility quality grids, that's the whole reason of being for this device. And so we're kind of showing the protected loads panel in the middle between the Sunny Island and the PV inverter. Again, in grid tie mode, the Sunny Island by default will allow excess PV power. If there's more than the loads need, more than the Sunny Island needs to charge its batteries, the excess will be allowed to backfeed to the grid. But that is a user adjustable parameter that can be set to 0 or turned off so that there is no grid backfeed depending on what the utility may require. If someone has an older PV, the system with the Sunny Island, and they had a PV system and a charge controller, we don't want to force them to have to buy a new inverter. They can couple that into the DC side of the Sunny Island. The charge controller output would have to be 48 volts for that to be compatible. And anytime there is something that touches the Sunny Island's battery bank outside of itself, the Sunny Island needs to know what the other thing is doing. Is it putting current into my battery bank? Is it pulling current out? Because it needs to update and adjust its charging regime to reflect that. So if something is touching the battery bank, a shunt which is really just a high precision resistor, very, very accurately measure current, needs to be installed in line and wired into the Sunny Island. The Sunny Island, almost everything that it does is driven by state of charge of the battery bank. And if it begins to detect that the battery is behaving in such a way that its real state of charge is vastly different than what the Sunny Island is assuming its state of charge is or calculating, then it will shut the system down. So if something is loading the battery bank or recharging the battery bank and the Sunny Island doesn't know about it, very, very quickly the calculated state of charge and the actual state of charge will diverge, and the Sunny Island will shut the whole system down. So if anything is touching its battery bank besides it needs to know. Very, very smart machine, and it realizes if reality is different than what it calculates, it's not really safe to continue. The Sunny Island operates a AC microgrid if it is isolated from a utility grid, and it is controlling now, it's creating that 120 volt, 60 hertz AC utility power that is powering the microgrid. If there are PV inverters on that grid, it's possible that there may be excess power. The PV inverters are producing more than the Sunny Island needs to power its loads or charge its batteries. The way it controls power sources on its microgrid is by frequency shift power control, FSPC. If it sees more power than it needs, it will raise the AC frequency from 60 hertz. And SMA Sunny Boys are smart enough to respond to that linearly. And now even in the United States, there are large areas where utilities require grid-connected PV inverters to be able to respond to FSPC that is actually implemented by the utility. If that utility grid frequency goes up, the inverters need to respond by throttling down their active power. So this is a power, it may be called freq watt for frequency and power watts. So SMA inverters can do this. Now more and more grid-tied inverters have this capability, whether or not it's enabled. And so it's a very effective way to throttle excess power down. And if the inverters can respond linearly, then the Sunny Island can make them come down to whatever active power exactly meets the load demand and the charging demand on its microgrid. So it can exquisitely balance the loads and the sources. If the PV inverter is set to simply turn off once the frequency gets too high, that will still achieve the result that the Sunny Island is looking for. The excess power will go away, but now the loads may require, let's say, 1,000 watts. So then the Sunny Island will have to pull from its battery bank to provide that power. So it's less elegant, but it still works very, very effectively. So just a quick overview. In grid-tied battery backup, the Sunny Island, it is a UL 1741 listed device. So just like a PV inverter, as long as that utility grid is within spec, it will operate and interact with that grid. And in this case, it can pass power across its isolation relay to the protected loads panel. If that goes out of spec for frequency, for voltage, very, very quickly, the Sunny Island will open its transfer relay, isolate everything downstream, that is the protected loads panel, from the faulted grid, and within a maximum of 35 milliseconds, take power from its battery bank, create the 120 volt, 60 hertz grid to power that protected loads panel. So most users and most loads will never even notice this transfer time. So very, very quickly, it will step in and become the utility grid. So a grid-tied PV system without any type of Sunny Island works very, very well. But as soon as the grid goes away, the inverter says, okay, it's not safe for me to export power, even to the home that it's attached to. So there aren't many options for allowing a grid-tied inverter to provide power without battery backup system. SMA Secure Power Supply is one of the very few that can even do that. So lots of people would use a battery backup system to allow the PV to continue working, but they don't even need the PV to have the system work. The simplest setup would be a Sunny Island, a battery bank, providing power should the grid fail. So this Sunny Island is sitting there watching the grid. Whenever the grid fails, the isolation relay will open. The panel behind it will get, now if we're showing a single Sunny Island, 120 volt, 60 hertz power. But in this scenario, there's no way for the batteries to be recharged when the grid is gone. So that's not the most useful case. There are use cases, and this is the simplest use for the Sunny Island is straight battery backup. So there is some amount of power, but for as long as the batteries have power. To have a PV system stay on, if the homeowner doesn't need more power than a single Sunny Island, it's possible to use an autoformer to have a single Sunny Island create a 240 volt microgrid, which would allow the PV system to provide full power when the utility grid has failed. So now again, if the grid has failed, the transfer relay will open, but the autoformer will allow the Sunny Boy, shown in this picture, to continue to function. SMA does not make our smart former, which had this autoformer capability, but we have sold to Midnight Solar the same autoformer that was in that. They have placed it in a yellow container that has the same curvature and the same color as the Sunny Island. So the device on the top of this panel shown here is an SMA autoformer in Midnight's enclosure. The device below it is SMA Sunny Island. Midnight Solar makes the back panel, the AC and DC connection panel at the bottom. So there's a DC circuit breaker for the battery isolation, and there are AC breakers for the output of this system. And again, this one system with a single Sunny Island and autoformer will allow up to 6,000 watts, but at 240 volts. It's a fairly tall panel, and the Sunny Island is a fairly heavy device, so definitely it's a nice beefy plate to hold all of this securely. But Midnight likes the Sunny Island very, very much, and they provide lots of good accessories to work with it. But again, having the autoformer, if the grid fails, the autoformer output is 240 volts. A PV inverter for split phase will see a good, quote unquote, utility grid and be able to provide full power to provide for loads and to recharge the batteries. If this system is sized correctly, that could operate indefinitely. If you have a PV system that can power all the daytime loads and recharge the batteries during the day, then the Sunny Island and its battery bank potentially could run those loads at night, and you just keep repeating. Obviously, there will be situations where the PV system won't be able to provide that much power. Maybe whatever caused the utility grid to fail damaged the PV array, or there's just several days of very bad weather. Most systems will want as many potential sources of power to be available should the grid fail. So often, very often, you would have a generator as well. And we're showing to the left the grid and the generator come into something labeled ATS, automatic transfer switch. That transfer switch can be automatic, it can be manual, but some way of switching between utility power and generator power, and the output of that switch needs to come to the AC2 terminals of the Sunny Island. And again, in this scenario, that dig-in input to the Sunny Island does need to be wired to tell the Sunny Island when the AC2 source goes from grid to generator. It actually opens up some frequency and voltage parameters, prevents backfeed in the case of the generator. So it does some important things. And there is a tech note explaining how to wire that that is available off the product page, and we can provide to everyone who's in attendance. Some folks will use the Sunny Island as a full home backup. They don't want to have power from the grid run through the Sunny Island to the loads. They don't want the PV power to have to run through the Sunny Islands. They have the Sunny Islands as a kind of a generator backup. The grid will charge the batteries for the Sunny Island while it is present, and as soon as it fails, you see this diagram, the transfer switch is switched over to where the Sunny Islands now are powering the full home panel, and now all of the PV power from those two Sunny Boys is available on that home panel. For 6,000 watt Sunny Islands, their actual full, the 3-hour rating is 6,000 watts. The full continuous rating is 5,750 watts. 4 of those running continuously is 23,000 watts of just battery power. 23,000 watts is close to 100 amps continuous on a 240 volt panel. That really is truly getting close to whole home backup. Most homes don't pull 100 amps from the utility grid. And that's just the battery power that the Sunny Islands can provide. With PV support, you can scale up to close to 50 kilowatts. And that would be the daytime maximum for a 4-stack of Sunny Islands. So I'm talking about this cluster of more than one Sunny Islands. I want to be very clear on what that means. One or more Sunny Islands is referred to as a cluster. When you program these devices, One device is labeled as the master, programmed as the master. All of the Sunny Islands have that functionality, but setting the others as slaves means they will take cues from the master, and the AC waveform outputs of multiple Sunny Islands will be synchronized so that all of the AC power of multiple units can be driven to one loads panel, and a split phase or three-phase grid can be easily created. An important thing to remember is each cluster of Sunny Islands must wire to one and only one battery bank. Again, the slaves all just listen to the master. A cluster can be a single phase cluster where 1, 2, or 3 Sunny Islands, their AC waveforms are perfectly synchronized, so it's all 120, 60 hertz output. Or they can be told they need to create a three-phase grid, and that would be a 120, 208 three-phase grid. Pardon me. Or it can be a split phase grid where you can have 2 or 4 Sunny Islands, and the output of those will create a 120, 240 split phase grid. So there are lots of options for scaling up. So the maximum size then for a 4 6048 Sunny Island split phase grid would be 23,000 continuous watts just from battery power and the Sunny Islands alone. You can scale up quite a bit of PV to add to that. All of that AC output synchronization is simply done by communications between the master and the slaves. And the black RJ45 cables that allow that are included in the box with every Sunny Island. So it's simply wiring those comms cables and programming at commissioning. Every Sunny Island out of the box is capable of being the master, and it's simply a programming choice. Sunny Island microgrid operation is generally driven completely by the state of charge of the battery bank. The master will monitor the state of charge of its cluster's battery bank and will really dictate what happens with the cluster. If the state of charge gets too low, the Sunny Island will shut down the whole microgrid to protect the health of its battery bank. So its primary goal is to maintain the health of its battery bank, not actually operate a microgrid. As batteries age, the state of charge, that is the amount of charging they can do, might reach 100% before the nominal capacity at day 1 is reached. That is, the battery ages and it becomes, in essence, a smaller gas tank. It can't hold as much fuel, as much energy as it did on day 1. But there's no point in continuing to try to dump current into it because it can't hold anymore. So this state of health metric is monitored also by the Sunny Island. So if the 100 amp hour battery bank on day 1 can only hold 80 amp hours 5 years down the road, the Sunny Island is smart enough to know that once 80 amp hours of energy have been put into it, its state of charge is 100% because the state of health is only 80%. And there's no point in continuing to try to charge it. So while it is driven by state of charge, it's smart enough to adjust based on state of health that an aged battery can't quite hold as much. We don't have an approved list for lead acid batteries for the Sunny Island. All we really require is that nominal voltage of 48. It is very nice that there are many, many reputable manufacturers and they build batteries for different use cases. Off-grid would be daily cycling, whereas battery backup would be much more infrequent cycling, but it might be deeper. And the manufacturers can build the electrode plates to actually fit either of those use cases. Most lead acid batteries you're going to find in 12 volt or smaller monolithic units, and you need to wire those in series so that the series adds up to 48 volts. Most 12 volt batteries you're going to find in lower capacity. If you want to get to larger amp hour capacity, you're going to be going down into the 2 volt range, and then that's 24 batteries in series to get that 48 volt. Once you have the maximum capacity in a string, the only way, if you want to add more amp hours, is putting strings in parallel. So on the bottom part of the diagram, we're showing 2 strings that would be 100 amp hours at 48 volts. If they're wired in parallel, that's doubling the amp hour capacity. The Sunny Island treats that battery bank as a monolithic unit. It provides charge current, but it doesn't know where that goes. If there is a bad cell in one string, especially if there's limited charge current, if you don't have the unlimited current of a grid, the bad actor will begin hogging that charge current, and the strings will become unbalanced in state of charge. So SMA recommends no more than 3 strings going to a Sunny Island cluster. So that generally will limit your battery bank capacity size. And most likely it will be significantly smaller than 10,000 amp hours. And this is showing the breaker or fuse between the island and battery bank requirement. And Midnight Solar, again, makes DC circuit breakers that fit the correct sizes quite well. There are also lithium-ion battery banks that are on the approved list for the Sunny Island. The lithium-ion batteries must be on the approved list because that is testing the battery management system of that battery in conjunction with the Sunny Island. They work correctly because now the battery management system must handle accurately the lithium-ion battery. There are devices that have been used very well with the Sunny Island that are not currently on the approved list. The company called Blue Planet makes a blue ion battery that has been used quite a bit in Puerto Rico with the Sunny Island very successfully. And Discover Battery has a battery that has also been used very, very well with the Sunny Island. Neither of those devices is currently on the approved list, but both are undergoing testing. I believe the Blue Planet device should be on the list fairly shortly, and hopefully the Discover battery won't be too much further down the road. Those are pretty attractive choices, and we are looking forward very much to having them on the approved list. Each cluster of Sunny Islands, even up to 4, must connect to 1 battery bank. So looking back at the lead acid system, if you have 3 strings of batteries wiring to 4 Sunny Islands, those need to be paralleled at some point. Big Polaris lugs is not going to cut it for a large system. Generally, the battery strings should come together on a large bus bar and then branch out to the 4 Sunny Islands. The insert picture shows a combiner box from Midnight Solar with 1,000 amp rated copper bus bars there in the center to do exactly that. If you have big systems, you'll want large bus bars where you can bring in the large wiring from the battery bank and out to the Sunny Islands into that enclosure. That has a built-in shunt, and you can see in the lower right, it has the circuit breakers for disconnection of the batteries. So very, very nice setup for larger systems. For lead acid batteries, the battery temperature sensor is included with the Sunny Island. It only needs to be wired from the master to the battery bank and placed at a place in the battery bank that will give it a good temperature reading. If it is disconnected or becomes cut, the Sunny Island will flag a warning. It will shut the microgrid down briefly and restart it, and then it will run the battery as if it was at a much higher temperature at 40 C, because it wants to be very conservative. It doesn't really know the temperature. For the lithium-ion batteries, the communication cable from the battery management system to the Sunny Island will bring in that temperature information. So it is only needed for the lead acid battery banks, and you only wire the temperature sensor from the master to the bank, even if there are multiple Sunny Islands. We have barely scratched the surface of what the Sunny Island can do in 40 minutes. I want to, again, emphasize that it is very straightforward to set up a Sunny Island system. And we have several documents. One of the tech tip videos, I think, is the easiest way to walk through this quick configuration guide. If you have a multiple Sunny Island system, the slaves are configured first because it's a 2-step process. You tell them what grid they're going to be part of to create, be it a split phase grid, single phase grid, or 3-phase grid, and then tell them they're a slave and which slave. And then they're just waiting for the master. So the slave configuration is 2 steps. And then whichever device you have designated as the master, you configure it. You tell it what grid it's going to be a part of, and then that it's a master. Then it will ask for date and time. It'll ask, oh, am I connected to a grid or a generator? How much current should I pull from them? And a few more settings, but it's really only about a 10 or 11 step process, depending on your sources, for the master to be configured. And all of that information, what type of batteries they are, the amp hour capacity, will begin to fill out with default values, those 200 parameters for the Sunny Island system. The only default choices I do not agree with the Sunny Island is the battery protection mode 3, well, actually 2 and 1 state of charge triggers. There are 3 levels of panic for the Sunny Island when its state of charge gets down below a certain threshold. You go into battery protection mode 1, which is very noticeable for the operator of the microgrid. and there should be plenty of time to react from that scenario until the system reaches battery protection mode 3, because that requires really recharging the batteries manually. The default state of charge for battery protection mode 1 is 20%, for 2 is 15%, and 3 is 10%. I would strongly suggest setting that battery protection mode 1 trigger to 40%, 50%, something very, very high, where there's plenty of reaction time for a system operator to correct whatever problem is causing the protection mode to be entered before you get to protection mode 3. That is the tech tip video link there for walking through the quick configuration guide of the Sunny Island. I don't want to spend too much time more on the presentation to give time for questions, but one thing that is unfortunately a bit of a pain point for the Sunny Island US right now is the communication structure. The Sunny Island US only has RS-485 as a communication choice. All of our other inverters, our PV inverters, the Sunny Boy storage battery inverter, now speak over an Ethernet communication-based protocol. So there has to be a translator from, if you have Sunny Islands and Sunny Boys in the same system, translate from the RS-485 of the Sunny Island to the Ethernet-based that the Sunny Boys will use and required for sending data to our Sunny portal. The COM gateway shown in this picture is that translator. Unfortunately, and it can gather data from RS-485 SMA devices as well as SpeedWire, the Ethernet-based devices. The COM gateway cannot register directly to the Sunny portal. So right now, it's slightly painful to send data to SMA Sunny portal. You can see in this diagram, I have the COM gateway at the lower center, and to the top left of that is a device called the SMA Data Manager. That is the device that can register these devices to SMA Sunny portal. So currently, it requires both of these devices to register a system with SMA inverters and the Sunny Island US to the portal. Very shortly, I believe next quarter, there is an RS-485 port on the data manager that will be supporting SMA's RS-485. When that occurs, the COM gateway requirement goes away. You're down to one device that is required to register all of these SMA inverters to the Sunny portal. We'll definitely make a lot of noise about that when it occurs, but it should be a few months out at most. So that is the real pain point, I think, now, is sending all of this data to Sunny portal. There is free software from SMA that allows local monitoring directly through the COM gateway. The COM gateway is less expensive than the data manager, so if local monitoring is all that is required, Sunny Explorer and the COM gateway can be a option. And this is all just wiring, showing where the RS-485 piggyback card goes in, the master Sunny Island. So if you have several Sunny Islands and you're monitoring them with the COM gateway, only the master device needs the RS-485 piggyback. And then the rest is wiring to between Sunny Island devices and then off to the COM gateway. These are some pictures we'll provide this presentation here in the accessories bag to do that RS-485 wiring between the master Sunny Island and the COM gateway. And again, that can be done locally. And this is a screenshot of Sunny Explorer showing local monitoring. And this is a device on the Sunny portal, very, very nice system up in British Columbia that has been on Sunny portal for, gosh, maybe close to 10 years now. A very, very nice Sunny Island system. I want to close with 3 slides or 4 slides before I get to questions, some guidelines for sizing. The guideline at the bottom of this screen is actually not a guideline. This is a hard and fast rule. The isolation relay in every Sunny Island US is rated to 56 amps. That is going across it from the grid to the protected loads panel, and that current draw is dictated and controlled by the Sunny Island, so it will be respected. But it is also the limit for power coming from the AC1 side, the protected loads panel side, back to the grid. So if PV power is allowed to be backfed through the Sunny Island to the grid, that cannot be more than 56 amps for each Sunny Island. And that's 56 amps at 120 volts or 6,720 watts. So for each Sunny Island, because each Sunny Island has one of these relays that can handle part of the load, no more than 6,720 watts of PV power can be on the protected loads panel. If you have 4 Sunny Islands, that means you can have 26,000 some odd watts of PV power on the protected loads panel. And again, the concern is only when that is grid tied. If this is an off-grid system, no PV power will backfeed across that relay, because if there's a generator on the other side, the Sunny Island is not going to allow backfeed anyway. So it is only a concern for a grid-tied system, but that is a hard and fast limit. The rule of thumb for off-grid systems would be no more than 2 watts of PV power per watt of Sunny Island power. You don't want the Sunny Island to have to throttle the PV system back and forth all day. Another guideline, and again, these can be changed based on local microgrid power requirements, is a minimum of 100 amps hours of battery capacity per kilowatt of PV. And you can see the math here on this slide. A 1,000 watt array should provide roughly, in a 5 peak sun hour environment, 5,000 watt hours of power. And that is roughly what would take to charge up a 100 amp hour battery bank at 48 volts. So it's roughly a day's storage of a kilowatt of PV array in a 5 peak sun hour environment. So again, there may be reasons that this can be adjusted one way or the other, but a good rule of thumb. If there's a generator in the system, generally a quote unquote dumb generator, somewhere right around the same nameplate of the generator as the sum of Sunny Island powers is what we would like to see. If it's a newer inverter style generator, we would actually ask for twice the nameplate on that generator than the sum of the Sunny Island powers. That will allow that inverter generator to operate far more beneficially. We've seen problems with smaller inverter generators. So again, those 2 rules of thumb are based on the operating style of the generator, and the generator white paper that I call out in this last bullet point is a technical document on the Sunny Island US product page that talks about what styles of operation of generators are compatible and sizing requirements or guidelines. And the last one's pretty straightforward. Every watt of load you want to run when the grid is away, have a watt of Sunny Island capacity to do that. That one's pretty straightforward. So with that, I want to open up the floor for questions. I want to leave a little bit of time, and hopefully I've left, about 10 minutes for folks to ask questions. But the Sunny Island, again, in summary, should be considered a battery-based inverter that is usable as off-grid or grid-tied battery backup, can be used without PV or retrofit into a system with PV or added at the same time as PV. Has quite a bit of capacity just from the Sunny Islands for battery power, so really is capable of whole home backup and can access very, very large battery banks. So with that, any questions that I can handle?
Thanks, Mike. That was a great overview. We do have one question here, and it's why was the vent fan control removed from the aux relay control?
I was unaware that I'm assuming there's a bat fan that was a default setting for one of the relays, so that if you hit a certain charge cycle and you thought, okay, I have a lead acid battery bank where there could be quite a bit of hydrogen being generated during this charge cycle, that you could trigger a fan to come on automatically when that part of the charge cycle was entered. If that's the question, I was unaware that choice was actually taken away. So I can follow up on that. If somebody has maybe is a firmware for the Sunny Island that they've seen that go away, that would be great. And I don't know, there is a multifunction relay in the Sunny Boys. There are some settings for that. So love to confirm that someone is talking about the Sunny Island and the 2 programmable relays and having that bat fan setting, or is it one of the default settings removed? And then if so, if there's a firmware version that they've seen it in, and I can investigate.
Okay, the next question is do you need the RS485 cable between the Sunny Boys 6 and the Sunny Island to share AC coupling communications? So
no, the AC coupling, what we used to have is that the Sunny Boys, you would wire RS485 communications to dynamically change Sunny Boys from grid tied mode to, in essence, off-grid mode when the Sunny Island sensed a loss of grid. Our Sunny Boys now do not have the capability of being wired up for RS485 communications. But if the Sunny Island is in front of them and that is a UL1741 device, having the Sunny Boy set to off-grid mode, it will have wider voltage and frequency settings. But if the grid goes out of spec, the Sunny Island will isolate it as well as itself from the faulted grid. So this is what we've been requesting or recommending to installers. And I don't believe there's been pushback from inspectors that you have the Sunny Boy that is not with the grid tied settings, but the Sunny Island is between it and the grid, and it's enforcing the UL 1741 limits. So that is the way of having the Sunny Boy be able to still very, very elegantly respond to the frequency shift power controls when the Sunny Island is in charge, rather than just, it's either producing full or it's off.
Do you want to just expand on the frequency shift power control a little bit more, if you don't mind, and just how?
Yeah. So again, when the Sunny Island is actively creating the microgrid, it's in control of setting voltage and frequency. And if it sees there is more, let's say, PV power on its microgrid than it needs for the loads, it sees power coming back to it. It doesn't need it to charge the batteries. It raises the AC frequency from 60 hertz upwards to get rid of that excess power. A standard quote unquote grid tied inverter at 60.5 hertz, above that, the grid is seen as bad. And so the inverter must stop exporting power. So the PV inverter would go from whatever it's producing to 0 watts. The excess power has been removed, but it's not as elegant as having the inverter respond between, and this is what the Sunny Boys are set to as default and off grid, between 61 hertz, let's say it was producing 3,000 watts. It will go from 3,000 watts to 0 watts linearly between 61 hertz and 62 hertz. So the Sunny Island for frequency shift power control will go above 61 hertz and keep rising until it sees 0 net backfeed coming to it. The PV power is allowed to exactly balance the load demand and the charging demand. And so the Sunny Island will range the AC frequency between 61 and 62 hertz to achieve that. It doesn't then need to pull from battery power to provide for the loads. It simply controls the PV power.
So I know your preference would be to use a Sunny Boy with the Sunny Island, but what if there's a situation where there's an existing grid tie that's a non-SMA product and you want to use the Sunny Island to AC couple with that?
Exactly. So what been in are that 0.5 hertz. Then when the frequency goes above that, the output of that PV inverter goes to 0. So that would be usable with the Sunny Island. Again, now when the Sunny Island raises that AC frequency, whatever the PV inverter was doing past 60.5 hertz, that goes to 0 watts. So if there's still 1,000 watts of load on the protected loads panel, now the Sunny Island needs to pull from the batteries to power that, but the system operates very, very well. It's just not as elegant as a linear throttle of power. It's the PV inverter is providing, or it's not. So it will work completely correctly. One thing I would advise though is if installers are doing that, if it's not an SMA inverter, verify with the manufacturer of that PV inverter that they don't have any warranty concerns with utilizing their PV inverter in an AC coupled microgrid. Some manufacturers have had concerns. And again, their inverter has to work this way if the utility grid is doing that frequency change or a Sunny Island. So there should not be a warranty implication. But again, I think for installers to best protect the interest of their customers, they should verify with the manufacturer if it's not an SMA PV inverter. So technically it will work correctly, but to provide maximum coverage, I guess, for the homeowner or the existing PV system owner, make sure there's no warranty implication for implementing it in an AC microgrid.
Great. The last question is about the sort of little microgrid image that you had up there. When you have that situation, could you have other Sunny Islands deployed elsewhere on that grid, and would that still enable the frequency shift power control?
I want to be very clear on this. So generally, yes is probably the answer, but let's back up. I'm not sure exactly what. Let's see if it was, where's the pretty picture? I'm really backing up here. So there would be, for this scenario, one group of Sunny Islands. So we see the 3 Sunny Islands in the building with the generator. So this would be a 12208 3-phase AC grid. All of that, the AC waveform here is controlled by the Sunny Islands until such time as the generator comes in. All of this, those 3 Sunny Islands share that battery bank that is to the right of the group, and their AC output would provide microgrid power to some set of loads. If you wanted to double the number of houses in the scenario, and there was more power than those 3 Sunny Islands could handle, what you need to do is just make sure that the loads panel and all of the PV systems that are added, those would be consolidated on a separate AC loads panel that a separate cluster of Sunny Islands would manage. Both groups of Sunny Islands can access power from the same generator or the same grid, but they will have a separate battery bank and they will power separate loads panels. There is a device called the multi-cluster box that can take multiple groups of Sunny Islands. And for the US device, it's multiple groups of 3 Sunny Islands. So it's a 3-phase device, and it can take power from 1, 2, 3, or 4 clusters of Sunny Islands and provide that synchronized to one loads panel. But that is really needed if you have more than 17,000 watts of load that must be driven to the same load and cannot be subdivided. Otherwise, it's much more direct to simply segregate the loads into separate loads panels that each have their own cluster of Sunny Islands, and the multi-cluster box is not required. So I'm not sure that that really answers the question, but each group then, the master Sunny Island of that cluster, can handle frequency shift on its microgrid. It would not impact the other microgrid.
Perfect. Well, that's all we have time today for questions. So I really appreciate what you did, and it was great having you, and that was a really good overview. So
Awesome.
Thank you.
No, definitely appreciate it, and thank you, everybody.
Okay, thank you.
Awesome. Take care. Bye-bye.